Light has no mass, zero. A photon, the particle of light, has no rest mass, none. And gravity, as Newton described it, is a force that acts on mass, more pull, less mass, less pull, zero mass, no pull at all. So here's the problem. Light bends around massive objects. We've measured it, photographed it, built entire telescopes that depend on it. Gravity bends light. But light has no mass, so how? If gravity is a force that acts on mass, and light has no mass, then one of two things is wrong. Either gravity isn't what Newton said it was, or the universe is doing something deeply strange. Einstein's answer was both, and it's stranger than anything Newton imagined. Gravity isn't a force, it's geometry. And once you see that, everything changes. Newton's theory of gravity works. That needs to be said clearly because it's easy to dismiss it once you know it's incomplete. Newton predicted planetary orbits. He predicted tides. He explained why cannonballs follow parabolas and why comets return on schedule. For 200 years, nobody needed anything more. The predictions are right for slow objects in weak gravitational fields. But Newton himself was deeply uncomfortable with what he'd written. He could describe gravity with extraordinary mathematical precision. He could not explain what it was or how it worked. "I feign no hypotheses," he wrote. He meant, I can tell you the rule, I cannot tell you the mechanism. The mechanism he couldn't explain is action at a distance. The Sun is 150 million kilometers away. How does Earth know it's there? How does the gravitational pull travel across that vacuum? In Newton's theory, it doesn't travel, it's instantaneous. The moment the Sun moves, every planet in the solar system feels it, simultaneously, regardless of distance. That's a problem. Einstein's special relativity established that nothing, no particle, no signal, no information, travels faster than light. Instantaneous action across 150 million kilometers isn't just unlikely, it's forbidden. Newton's gravity was a perfect description wrapped around an unexplained mechanism, with a built-in violation of relativity sitting quietly in the foundations. The cracks were there from the start. Einstein found them. Einstein is working at the patent office in Bern, not yet the famous figure, that comes later. He's thinking, as he often does, about what the equations mean physically, not just mathematically, physically. He imagines a man falling off a roof. During the fall, before impact, the man is weightless. Everything around him floats. If he drops his keys, they fall alongside him. If he's in a sealed box, he can't tell, from inside the box, whether he's falling in a gravitational field or drifting in outer space with no gravity at all. The physics is identical. Einstein recognized this wasn't an approximation or a quirk. It was exact. And the reason it's exact comes down to a strange coincidence in Newton's theory that Newton never explained. In Newtonian mechanics, mass appears twice. Gravitational mass, how strongly gravity pulls you. Inertial mass, how hard you are to accelerate. These are conceptually different things. One governs gravitational interaction, the other governs resistance to force. They don't have to be equal. But they are equal. Every experiment ever performed confirms it, to 1 part in 10^1015. Gravitational mass and inertial mass are the same. In Newton's theory, this is a coincidence. There's no explanation. It just happens to be true. Einstein decided it wasn't a coincidence. It was a signal. The equality is exact because free fall and zero gravity aren't just similar situations, they're the same situation. Gravity and acceleration are the same thing, described differently. You can always locally transform away gravity by going into free fall, or fake gravity by accelerating. He called it the happiest thought of his life, the equivalence principle. And from that single idea, that free fall and weightlessness are physically identical, the path to general relativity begins. Special relativity had already done something remarkable. It merged space and time into a single four-dimensional structure, spacetime. Not space and time running in parallel, one unified thing, where the division between space and time depends on how fast you're moving. But spacetime in special relativity is flat, fixed, a rigid background, the stage on which physics performs. The stage doesn't care about the performance. It doesn't respond. Einstein's next move took a decade. What if the stage does respond? What if mass and energy curve spacetime itself? What if what we call gravity is just the geometry of curved spacetime? The rubber sheet analogy gets used a lot. A heavy ball placed on a stretched rubber membrane causes a dip, and smaller balls rolling nearby curve toward it. It's a useful picture for curved space, and it captures something real. But it's importantly incomplete, because it shows curvature in 2D, and it uses gravity to explain gravity. The real curvature is four-dimensional and includes time. The time part is the part that matters most. Clocks run slower in stronger gravitational fields. Not because of any mechanical effect on the clock, not because gravity is physically slowing the gears. Time itself flows at different rates at different positions in curved spacetime. This is gravitational time dilation, and it's been confirmed so many times in so many experiments that it's built into everyday technology. GPS satellites orbit at about 20,200 kilometers altitude. Gravity is weaker there than on the surface. Weaker gravity means faster running clocks, by about 45 microseconds per day. Special relativistic effects from their orbital speed slow them back by about 7 microseconds. Net result, satellite clocks run about 38 microseconds fast per day relative to clocks on the ground. Without correction, positioning errors would accumulate at roughly 10 kilometers per day. The correction is applied continuously. The system works because general relativity is correct. Your head, being slightly farther from Earth's center than your feet, experiences slightly weaker gravity. Its clock runs slightly faster. Over a 79-year lifetime, your head has aged about 90 nanoseconds more than your feet. This is not a thought experiment. It's a measurable fact about how time works in curved spacetime. Mass and energy curve spacetime. Curved spacetime tells mass and energy how to move. That's general relativity. Now, why does light bend? Light always travels in a straight line. This is not approximate. It's the definition of what straight means in spacetime, a geodesic, the path of shortest proper time between two events, the natural trajectory of anything moving through spacetime when no forces act on it. Near a massive object, spacetime is curved. The geodesic, the straight line, through that curved spacetime is not a straight line in the flat Euclidean sense. It's the straightest path available through a bent geometry. Light follows that path, not because gravity reaches out and deflects it, not because photons are secretly massive, because that path is the straightest thing available. Light is doing exactly what it always does. The geometry changed underneath it. Here's an analogy that captures the mechanism better than the rubber sheet. A plane flying from London to New York follows a route that looks curved on a flat map. On a Mercator projection, it arcs northward toward Greenland. But the plane isn't being deflected. It's flying the shortest possible path on the surface of a sphere. The straight line on a curved surface looks curved when you project it flat. Light near a massive star is doing the same thing. From far away, from a flat coordinate system, the path looks curved. From the photon's perspective, from the geometry of the spacetime it's actually moving through, it went straight. The bend is in the geometry, not in the photon. This is not a semantic distinction. It has real, measurable consequences, and the most famous measurement of it changed the course of physics. Einstein publishes the final form of general relativity in November 1915. Among its predictions, starlight passing close to the Sun should be deflected by 1.75 arcseconds. An arcsecond is 1/3600th of a degree. This is a tiny angle, but measurable. Newton's theory also predicts a deflection if you treat light as a particle with some effective mass moving at c. That Newtonian prediction is 0.87 arcseconds, exactly half of Einstein's value. The factor of 2 difference comes from the fact that Einstein's spacetime curvature affects both the spatial component and the time component of the path, while Newton's calculation only gets the spatial part. The problem is obvious. You can't see stars near the Sun. The Sun is 400,000 times brighter. Except when there's a total solar eclipse. Then the Moon blocks the disk of the Sun, and stars close to the solar limb become visible for a few minutes. May 29, 1919. 2 British expeditions. One to Sobral in northeastern Brazil, one to the island of Príncipe, off the west coast of Africa. Both photograph stars near the eclipsed Sun. Both compare those positions to the positions of the same stars photographed months earlier at night when the Sun wasn't nearby. Arthur Eddington, on Príncipe, is working through clouds that part at the critical moment. The data is noisy. The analysis is careful. The results, announced at a joint meeting of the Royal Society and the Royal Astronomical Society in November 1919. The deflection is 1.75 arcseconds, Einstein's value, not Newton's. The next morning, Einstein is front-page news around the world. Revolution in science, new theory of the universe, Newton's ideas overthrown. The geometry of space had been measured for the first time. It was curved, and it was curved exactly as Einstein said it would be. This is the moment physics stopped being about forces acting across space and became permanently about the shape of space-time itself. That 1919 measurement, a few stars, a solar eclipse, a handful of glass photographic plates, grew into something nobody anticipated: gravitational lensing. When a massive object, a galaxy cluster, sits between us and something more distant, it bends the light from that distant object around it. The result can be multiple images, arcs, or, in perfect alignment, an Einstein ring, a complete circle of light around the lensing object, the distant source smeared into a halo by the intervening mass. These aren't curiosities, they're tools. Gravitational lensing lets us see objects far too distant and faint to detect directly. The lensing galaxy acts as a natural telescope, magnifying background sources by factors of 10, sometimes more. Some of the most distant galaxies ever observed were found through gravitational lensing. It maps dark matter. Dark matter doesn't emit or absorb light. It has no electromagnetic interaction. We can't see it directly, but it has mass. Mass curves space-time, and curved space-time distorts the images of background galaxies in ways we can measure. By analyzing those distortions across millions of galaxies, a technique called weak gravitational lensing, we can reconstruct the distribution of mass causing them, including mass we cannot see. The large-scale structure of dark matter in the universe, the cosmic web of filaments and voids, has been mapped using light that was bent by invisible mass. We're seeing the invisible by measuring its shadow in spacetime geometry. The same physics Eddington measured with a handful of stars on a cloudy island in 1919 is now mapping the invisible architecture of the cosmos at scales of billions of light years. General relativity keeps getting confirmed, aggressively, repeatedly, at higher and higher precision. Gravitational waves. Einstein predicted in 1916 that accelerating masses should produce ripples in spacetime, waves of curvature propagating outward at the speed of light. For a century, nobody detected them. The effect is tiny. A passing gravitational wave from a distant black hole merger stretches and squeezes space by a fraction of the diameter of a proton across a 4-kilometer detector arm. September 14, 2015. LIGO detects a signal lasting about 0.2 seconds. Two black holes, one about 36 solar masses, one about 29, spiraling together and merging 1.3 billion light-years away. The signal matches the predicted waveform from general relativity precisely. The detection is confirmed. Einstein was right again, a century later. Black holes. The Schwarzschild solution to Einstein's equations, found in 1916 while Schwarzschild was serving in the German army on the Eastern Front, described a perfectly spherical mass so dense that the escape velocity equals c. Inside the Schwarzschild radius, even light can't escape. The event horizon. In 2019, the Event Horizon Telescope, a global network of radio telescopes working in concert, produced the first image of a black hole shadow, the supermassive black hole in M87, 55 million light-years away. In 2022, the black hole at the center of our own galaxy, Sagittarius A star, both images match the predictions of general relativity. And yet, at the center of a black hole, the singularity, Einstein's equations predict infinite curvature and infinite density. The math breaks down. GR predicts its own failure at the place where it should be most relevant, at the Big Bang. Same failure. Infinite everything. The equations cannot describe t equals 0. Quantum mechanics governs the very small. General relativity governs the very massive. At the Planck scale, 10 to minus 33 middle meters, 10 to minus 34 3 seconds, both are simultaneously necessary. Applied together, they produce infinities that can't be renormalized away. The two greatest frameworks in physics are mathematically incompatible at the foundations. String theory and loop quantum gravity are the leading proposals for reconciling them. Neither has been confirmed by experiment. We don't have quantum gravity. GR is almost certainly incomplete. We use it anyway, because within its domain, it's the most accurate physical theory ever constructed. Here's the thing worth sitting with. You are not being pulled toward Earth right now. From the perspective of spacetime geometry, from the deepest description we have, you're the one being pushed off a straight line. The person in free fall, the one we'd normally say is falling under gravity, is actually the one moving in a straight line through curved spacetime. Their path is the geodesic. You, sitting in your chair, are being accelerated. The floor pushes you away from the geodesic. The surface of the Earth is constantly pushing you upward, away from the freefall path, into a curved trajectory through spacetime. Gravity, from this perspective, isn't pulling you down, the ground is pushing you up. This sounds like a word game. It's not. It has mathematical content, experimental consequences, and it's the reason the equivalence principle works. There's no local experiment you can perform that distinguishes being in a gravitational field from being in an accelerating reference frame, because they're the same situation described differently. Gravity isn't a force in the deep sense, There's no gravitational force field with a particle mediating it, the way electromagnetism has photons. There's spacetime geometry, and the geometry is sourced by mass and energy through Einstein's field equations, 10 coupled, nonlinear, partial differential equations relating the curvature of spacetime to the energy-momentum content. Those equations describe the relationship precisely. What they don't explain is why. Why does mass curve spacetime? Why does energy have this effect on the geometry of the universe? What is the mechanism at the deepest level by which matter tells space how to bend? We name it, we measure it, we use it to navigate satellites and image black holes and map the invisible structure of the cosmos. We do not know why it's true. Einstein spent the last 30 years of his life trying to go deeper, to find a unified theory that would explain not just the relationship between mass and geometry, but why that relationship exists and how it connects to the quantum world. He didn't find it, neither has anyone since. Light bends because spacetime curves. Spacetime curves because mass and energy are there. Mass and energy curves spacetime because that's what they do as far as we can tell, and the reason lives one level deeper than our best theory reaches. Every time we look, there's more to see. That's not frustrating. That's what it looks like when you're actually making progress, when the answers are real enough to point clearly at the next question. The geometry of the universe is curved. We know how it curves. We know what it does to light, to time, to the paths of planets and the shapes of distant galaxies. We've measured it to extraordinary precision. We're still asking, why? And that question, sitting there, just past the edge of what we know, is exactly where physics needs to be.